In episode 1, we stressed this new term ray rather than a vector. And we said that the ray existed in a 2D complex space. From what I saw, all our pictures were just on a plane. So that would be a real space. So where does the complex stuff come in, and why do we need a complex stuff? You notice that the ray is determined by relative magnitudes. Relative magnitudes of what? Relative magnitudes of the two complex vectors. What about the magnitude of the arrow? That doesn't matter, because only the direction indicates the state. Now, there's something missing here. Here's the other thing that determines something about this arrow that you can't really draw, and that's the complex part of or actually the imaginary part of the complex number, and that is relative phase. Now, phase of what? Well, the phase of the two vectors that define this ray. You have the two magnitudes, but you also have the phase. And the phase is the complex part of all this business. What if you talk about a phase change that occurs on both vectors, but the relative phase stays the same? Well, then if the relative phase stays the same, then this arrow's phase does not change. Now, how do we visualize a phase difference? A relative phase is like a relative rotation. You can change the length of this ray, but it's still the same ray. But the direction is what matters. The relative phase gives us a rotation number that defines this ray. Let's keep going here. Now, one thing I want to warn you about, and that is the use of this green arrow that looks like it's rotating outside the ray. Really, you should think about this rotation as inside the ray. We don't want to talk about translating axes around this arrow here, and think of it as internal, which is, that doesn't make a lot of sense, really, but that's the way we have to visualize this thing. Now, let's go back to this picture, which we dealt with earlier in this recording. Is we've got an alpha and a beta. Now, these are complex numbers, so these complex numbers have a magnitude and a phase. So the relative magnitudes would be the difference or the ratios between the R1 and the R2. Those are going to give it the direction. And then these two phases, the relative phase between this phase 1 and phase 2, will give us the internal rotation. So internal rotation, well, how do you, if it's a line, it's infinitely thin, and how do you rotate inside an infinitely thin thing? But these are, I told you this two-dimensional complex space was not going to be that easy. You have to challenge yourself on it. And look what I see down here. I see an eye. Now, what's that eye? Oh, that's the imaginary eye. As I close off this video, let's look at this diagram. This is a 2D representation of a complex space, which only two-dimensional complex spaces can be represented this way. But this is convenient because guess what? That thing, that internal rotation and that relative phase and all that, it shows up on this blooming thing. So look up here. If we look at the green arrow, that would be the direction if the ray was directly on that particular vector axis. Now you might think, oh, well, here's the 1 because that's perpendicular. Nope, 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 it's not that easy. You look down here from this center point, this is when the direction would be all the way on the 1 basis vector. What's the red arrow doing? Well, the red arrow is right in between these two. So if we would put this on the other diagram, this would be at a 45-degree angle between those two. But here it shows up as a 90. What? How could that be? How does that help? Well, okay, well, between these two and this, we can get a plane. And we can just have a great circle, and then the direction can go around negative and all this kind of stuff if we go around that way. But what about, why does it have to be spherical? Oh, I get it. When you go around this way, that's the relative phase difference between the two. So we have the relative phase going around this direction, and then we have the direction going up and down this way. So it's all built into this magical thing. So we'll continue to use this when we talk about two-dimensional space. Now, of course, when we get to infinite dimensional space, this isn't going to work at all.